All right, hi guys. Today we're going to talk about lesson number 8, which is section 1.7 in your book, and it's all about the transformations of functions. The good news is you've seen the transformations of functions every single year, again and again, so they should be very familiar to you. The bad news is that no matter how many times you see them, there is always the chance of mixing them up and making a mistake. So hopefully this PowerPoint will help you not to do that. So here is a list of all the transformations. We saw them very briefly in the previous lesson as well. Sometimes you're going to be asked to identify and use transformations using just f of x notation, and then sometimes you will apply them to specific functions like the cubic or the quadratic, etc. And we're going to see all kinds of examples today. So the first set of transformations is what if you want to move the graph up or down? You would do that by putting a plus or a minus on the outside, and then you of course follow the sign. Positive is up and negative is down. When you're trying to move the graph left or right, that happens inside the function, and you always do the opposite. So a plus c implies to the left, and a minus c would be to the right. Then let's say you want to reflect the graph. If you want to reflect the graph in the x-axis, you're going to put the negative outside of the function. If you want to reflect in the y-axis, you're going to put the negative inside the function. Those 6 things are what we call rigid transformations, meaning that they do not change the size or shape of the graph. They simply move it up, down, left, right, or reflect it. Then you have the 4 stretching and shrinking, which are called non-rigid transformations. And you're going to want to take note of those 2 words because not only in this lesson, but in the homework and on the test, it will note whether it's rigid or potentially non-rigid, and that will tell you if it's an easier problem versus a harder one. So for the non-rigid transformations, if you are trying to vertically stretch or shrink, that happens on the outside. And again, you follow what it says. So in the first one, if you want to stretch it and the value of a on the outside is greater than 1. And in the second example, if you want to shrink it and the a is on the outside, it would have to be between 0 and 1. Again, whenever you're doing something horizontally, and in this case, it's stretching and shrinking, it's the opposite. So if you wanted to shrink your function, you're actually going to have the value inside that is larger than 1. And if you want to stretch your function, you're actually going to have the value inside that would be between 0 and 1. So again, anything that has to do with horizontal is always on the inside, and it's always the opposite. Here's an example of those same transformations, but now applied to a specific function, which in this case is the absolute value. So over here in the left-hand column, it's got the words. Then again, it shows you the important notation using f of x. And then here are the actual examples using the absolute value. Pay close attention when you have to put things inside of the absolute value. Those are all your horizontal transformations versus when you put things outside. Those are all your vertical transformations. And then, of course, pay closest attention to your reflections. Inside is over the y-axis and outside is over the x-axis. Bunch more examples. So again, these are the rigid transformations, which means you are not changing the size or shape. So a big plus 2 means move it up 2. A minus 2 inside of the squared, inside of the parentheses, means you're going to move it 2 to the right. Here you have the cubic function. So a minus 1 means you're moving it down 1. In question B, this here means left 2 and up 1. Then again, reflection here. So here is your x squared. That's your quadratic. If you have a negative outside, that is simply a reflection over the x-axis. No change in the size or shape, simply upside down. What if I were to give you the quartic function, x to the 4th? So notice it kind of looks exactly like the quadratic, except it has a flatter bottom. Here are 2 examples. So the parent function is up at the top right. Then I give you 2 graphs, and I ask you, what are those equations? So over on the graph on the left, compared to the original, the graph is clearly facing upside down, and the vertex is moved up 2 units. So how do you say a reflection over the x-axis? That's the negative out front, and then up 2 units. In the second graph, what are the changes? Well, again, it's clearly upside down. hence the reflection over the x-axis on the outside. It also appears that the vertex was moved 3 units to the right, which is why you're going to have x minus 3 inside of the fourth. Remember, when you say inside of the function, it doesn't just mean inside parentheses. If it's a quartic function, it has to be inside of the fourth. If it's a square root function, it has to be inside of the radical. So if you have any question what it means to be inside, make sure that you ask so that you don't make that mistake again and again. Non-rigid transformations. This is where the stretches and the shrinking come in. So usually they're fairly easy to identify visually, but a little bit harder to identify algebraically. So now we have the absolute value function. That's our v here with a slope of just 1. If there's a 3 on the outside, the way that you would say that in words is it's a vertical stretch of 3, which means each of the y values is multiplied by 3, which is why this graph appears to be skinnier and narrower because it's rising 3 times as fast. The slope would be 3 as opposed to being 1 in the original. Here, there's a 1/3 on the outside. So that means it's a vertical shrink of 1/3. Each of the y values is reducing by 1/3, which is why this graph appears to be less steep than the original. Again, instead of having a slope of 1, it would now have a slope of 1/3. We're not going to do every single one of these, but these are questions you should kind of be able to identify for yourself. We went over the parent functions last time. So based on these 6 examples, could you, 1, tell me what the parent function is? 2, describe the transformations in words. And then could you make a quick sketch of each? When I say a quick sketch, it means I really only need to see 1 or 2 points. I don't need you to be precise. So for example, number 1, that is the cubic function. Compared to the original, it would be 3 units to the left and 4 units down. If you were going to draw me a quick sketch of a cubic that was 3 units to the left and 4 units down, usually 0, 0 is the most important point at a cubic. It would now be -3, -4, and then it would still look like a cubic. And again, that's what I mean by a quick sketch. I'm not really looking for more than 1 or 2 important points. So I'm not going to do all of these, but these are the types of questions you could see on an assessment and the types of questions you kind of should be asking yourself. So then there are a couple of warnings, a couple of special cases. So if you haven't written anything down to this point, this might be where you want to jot a couple of things down. So your first warning, if there are multiple changes to the y values in a problem, you always do the vertical translation last. So here's what I mean by that. -3 times the square root of x plus 8. There are 3 transformations. They're all happening to the y's. So you are going to do the plus 8 last. So this negative on the outside, that's a reflection over the x-axis. This 3 is a vertical stretch of 3, and then this 8 is up 8. When you're trying to graph this, you would first multiply the y values by 3, then multiply it by a negative to show the reflection over the x-axis, and then the last thing you would do is go up 8. So anytime you have multiple y changes, you're always going to do the up or down last. Similarly, what if you have multiple x changes? If you have multiple x changes, you are always going to do the horizontal translation last. The nice thing about all of these rules for transformations is they only work if you have a positive x. Take a look here. You have a negative x. That means you're not allowed to just use those handy dandy rules we've been going over unless you factor that negative out. Not out of the absolute value, but just away from the x. You can't just take it away from the x, though. You have to take it away from the 4 as well. So first order of business, if you do not have a positive x, is to factor out whatever is in the way, which in this case is a negative. So if I factor a negative out of each term, I get a negative times parentheses x minus 4. Again, you're not taking it out of the absolute value. You're just taking it away from the x. Now, if you were going to describe these transformations one at a time, this negative on the inside would reflect you over the y-axis, and this would be right 4. And again, according to this warning, you would first have to take any x value, reflect it over the y-axis, which means make it the opposite, and then you would do the right 4 last. So multiple changes, always do the up, down, and left, right last, and you have to have a positive x in order for this to work. One more like that. So the square root of 5x minus 10. Again, the transformation rules mean nothing as long as there is a 5 in front of that x. So factor the 5 out. Again, not out of the radical, just out of the 5x. Now that you have separated the transformations, this 5 would be a horizontal shrink of 1/5. Right 2. And according to our rules here, you're going to do the horizontal shrinking first and then always do the left and right last. So 3 very important warnings. Don't disregard them. A couple more just general examples. This is some random function f of x. So please make sure you're comfortable with notation, whether it's just f of x, g of x, or whether it's particular. Here, the function to start with, it's the absolute value of x squared minus 4. So that's the graph in red. Notice that that's a quadratic that has been all made positive. That's what the absolute value does. A 3 on the outside is a vertical stretch, which is why the green graph is narrower. A 1/2 on the outside is a vertical shrink, which is why the black graph is less steep. So another one, same graph, x squared minus 4. This 3 on the inside, remember that when it's on the inside, it's the opposite. So this is actually a horizontal shrink of 1/3, which is why the green graph is super skinny. A 1/3 on the inside, that is a horizontal stretch of 3, which is why the black graph is super wide. So be careful with those stretches and shrinking. Those are always kind of the ones that give the most issues to people. And then finally, the last thing you have to be able to do is you have to be able to write me an equation for a transformed graph. Here's where you're going to want to pay special attention to rigid versus non-rigid. If I tell you that it's only rigid, that means you can assume there is no stretching or shrinking, and these are much, much easier to do. So the original absolute value is there in green. I'm asking you for the equation of the red one. I'm telling you that the point 6, -4 is for sure the vertex. And because it's rigid, it means that there is no stretching or shrinking, which means you can write this answer simply by eyeballing it. So if f of x is the original, we're going to call the transformation g of x. Compared to the original, the absolute value graph in red is 6 units to the right. So how do you do 6 units to the right? You do x minus 6 inside the absolute value. How do you do down 4? Well, then you add a minus 4. So this here is my equation of g of x, which would be the graph in red. So this is actually quite simple to do as long as it is a rigid transformation only. Of course, that would be no fun if they were all rigid transformations. So here's an example where it could be non-rigid. So if it could be non-rigid, it means you have to check to make sure that there is no stretch or shrink. In order to do that, you always have to have a point on the graph to use. And so I'm going to tell you, in this case, you're going to use the point -4, 1. So on the left, this is the original parent function. Here's the transformed graph over here on the right. I'm asking you to write the equation. Now, some of you are going to be able to do that just by guessing and checking, or I guess just kind of by eyeballing it. But whenever non-rigid transformations are involved, you can be a little bit more methodical. So here's what I'm going to do. Based on the way that the graph looks on the right-hand side, I'm going to write in the transformations I'm absolutely sure of, and then I'm going to leave a variable for the things that I'm not sure of. So I know that this is an equation of a radical function. I know that compared to the original, it is flipped over the y-axis. So I am going to write this as the square root of -x, again, because I know that it was reflected over the y-axis. What I don't know is, was there a stretch or a shrink? It could have been horizontal. It could have been vertical. My advice, always look for the vertical one. That just always seems to be the easier way. So if there was a vertical stretch or shrink, there would be some number outside of the radical. I'm going to go ahead and use the variable a. So again, notice I wrote y instead of f of x, doesn't matter. And then I put in all the transformations I was sure of, which would be the fact that it was reflected over the y-axis. But now I need to know, was there some stretch or shrink? How do I confirm or deny that? Well, here's where you use the point -4, 1. So plug a 1 in for y. Plug a -4 in for x, which becomes a -4, which becomes a 4. The square root of 4 is 2. Which means that a equals 1/2. So it turns out that there was a shrink here, which means that my final answer is y equals 1/2 times the square root of negative x. And again, whether you make it y equals or g of x equals, that doesn't really matter. If you're wondering, well, what if you put the a on the inside? You would get a slightly different answer, but it would be equivalent. So obviously, I would give you credit for any correct answer, but my advice is look for the vertical stretch or shrink, which means put the a on the outside, because for some reason, that just always seems to be an easier way to do it. All right, one last problem here with the absolute value. So again, notice the absolute value is on the left. You're trying to find the equation on the right, and I'm telling you that you can use the point 2, -6 to assist you. So I'm going to go ahead and start by identifying the transformations that I know. So I know that this is an absolute value function. I know that compared to the original, it's down 2 units. And again, be careful, it's down 2 units because the scale is 2. Then it's upside down, so there was a reflection over the x-axis. And because there may or may not have been a stretch or shrink, I'm going to put an A out there to decide for sure. How do I know if there's a stretch or shrink? Well, now I'm going to use that point 2, -6. So -6 equals negative A times the absolute value of 2 minus 2. I'm going to add this -2 to the other side, which is going to give me -4 equals, and then the absolute value of 2 is 2, so that's going to give me 2A. I'm going to divide both sides by -2, which means that A is 2, which means my final answer for this problem is y equals -2 times the absolute value of x minus 2. And I say again, you potentially, if you put the A on the inside, you would get a slightly different, albeit equivalent answer, which would be fine. Again, my advice, always look for the vertical stretches and shrinks. That just seems to be a little bit easier. Also, if you're wondering, what if you don't put the negative on the outside? What if you just leave it as A? Well, that means that when you solve for A, you're going to get a negative for A. So either way, you're going to get the same answer. So when you go to try these problems, again, there's a couple of different ways you can approach them. I've shown you what I think is best, but certainly you do you. In conclusion, anything inside the function, of course, affects the x's, and you do the opposite, where anything on the outside affects the y's, and then you always do what it says. So here is homework number 8. Go ahead and copy that down. For anything that is highlighted in red, that means you only have to consider the rigid transformations, which means no stretching and shrinking. So I point that out because the problems will go a lot faster if you know there is no stretching and shrinking. And again, that's just something you're going to want to be mindful of for the upcoming assessment, whether it's going to be an easier problem or a harder problem. So just make sure that you're paying attention. All right. Thanks, guys, for tuning in, and we will catch you next time.